So how was the last assignment? Was it brutal?
Jeez. How? Is that bad?
Yeah, I think we had 2 tests and I did really. I know it's no good excuse, but I couldn't think sheet.
Okay. How did the others feel? Was it brutal?
It was trying to figure out what we needed to use. Yeah, kind of.
Mm-hmm.
More than anything.
It's basically what I'm trying to do, if you notice in the assignments, is make you go through the exercise that we cover in the class. The concepts are basically the same, but I switched the geometry. From if we did the flat plate in the class, you do the cylindrical one. If we did the cylindrical one, you do the flat plate. Right? So the steps are basically the same, but you need to work through the math once. I'm particularly worried about the last lecture because there was a lot of math in there.
There's also another side.
Wow. Can you read that?
Can somebody turn the light off? I think we should get started. Thank you. Oh, yeah, that's great. So, I don't know, is it the comfort of having the recorded lecture? I see that there are more absences now. People are...
Some people are skipping the question of a test next.
Yeah.
Like, they're worried about it for whatever reason and skipping the class.
Don't know why.
Okay. I should start, well, I mentally note down who is absent. Last lecture was pretty heavy, I think, because we covered a lot of steps. We went through the whole problem of setting up the cribbing flow and getting a solution. And it is very important, if you feel that just by listening to it you understand, you really don't understand the steps involved. So I would encourage you very strongly to go through and fill the intermediate steps and make sure that you understand the path that you need to follow in getting from the Stokes equation, the simplified version of the Navier-Stokes after throwing the inertial term. You should understand, of course, the reasons for why we do that or when you can do that. We'll talk a little bit about that today. But those are the so-called Stokes equation. Low Reynolds number equation. As Reynolds number goes to 0. And then we went through quite a bit of manipulation to get it into this form. And those are imposed axisymmetry that converts it into a 2-dimensional problem. Okay. And then we introduced the stream function and eliminated all the primitive variables. The variables that are called often primitive variables are the velocities and pressures. These equations are in terms of velocities and pressures. So we get rid of them and get the equation. It's the same equation in terms of a new variable that is the stream function. So we've seen the meaning for physical meaning for the stream function, and you should know, for example, what do we mean by this e square psi? Okay, how do you calculate that? So it's basically the same operator that is defined here operated twice on that variable psi. So that gives you effectively a 4th order partial differential equation. And then we said we need to convert the boundary conditions from velocities into stream function. We saw how to do that at both the surface of the sphere and as far away from the sphere. And in the theta direction, we really didn't worry about specifying boundary conditions because of the symmetry in the problem. So from sine square theta, we know that it's axisymmetric, and so we can construct a solution of the form that has sine square in it and then some unknown function in the radial position. And we solve for that unknown function and obtain this profile. So there is again a fairly tedious step involved in getting the solution to this differential equation in this form, applying the boundary condition. Now that is a solution for psi, the stream function, but of course psi is related to the velocities by definition. So once I know psi, I can calculate Vr, which is what this is. And once I know psi, again, I can calculate V theta from that definition, and that's what that is. Then we take these velocities and put it into the momentum equation and get the pressure profile. So this is a pressure profile over the entire domain from r equal to a to r equal to infinity in theta direction as well. And finally, the other major step is getting the drag force by plugging in this pressure profile here and then these velocity profiles into the shear stress expression. Okay, and then dotting it with n, where n is the normal to the surface. So, and then dotting it with k to get the kth component, that is the component of the drag in the direction of the flow. Okay, and that turns out to be this very familiar 6 pi mu ua. So, the next assignment that I'm going to give you is going to be something like this, which may be a fluid sphere, so that you work through all the steps. And I want you to do that. That's an opportunity for you to work through it on your own, filling in all the steps. Just replace the solid sphere with the fluid sphere. And of course, this expression will be different. It will involve the viscosities of both fluids, the fluid sphere and then the fluid that is surrounding it. Now, in the last lecture, I also pointed out that this is valid only in the limit of Re going to 0. So when you plot it as a drag coefficient against Reynolds number, you will find that the curve follows up to about a Reynolds number of 0.1. Beyond that, you will begin to see the deviation from that. The reason for that is the solution that the assumptions that we made about the solution, that it is low Reynolds number, is not valid. So by the time Reynolds number is about 1, you'll begin to see differences between this expression that CD equals 24 over RE. So what happens in reality as you increase the Reynolds number? What do you think would happen? As I increase the Reynolds number, the inertial terms will become more important. That's a term that we have neglected from the Navier-Stokes equation. And people have attempted, before the days of computers in the 50s, people have tried to develop an analytical method for getting corrections to the Stokes solution. So take Stokes solution as the basis and see whether you can find corrections to account for the effect of inertia. So we're going to look at some of those methods today. Okay, so any questions on that last lecture? I guess with an exam coming, you probably haven't had a chance to review that.
I have a question.
Yeah.
So when you find the string function psi, can we apply that definition to any two-dimensional flow?
Yes, any two-dimensional flow, you can define a stream function, and that will automatically satisfy the continuity equation. That is the main reason for defining the stream function, so that you don't have to worry about solving the continuity equation, because the stream function by definition will satisfy the continuity equation. So for any two-dimensional flow, you should be able to do that. Yeah. Now, the appendix in Happel and Brenner has these definitions for various coordinate systems. We have seen Cartesian and we have seen spherical. We will see today cylindrical one as well. And then there are other coordinate systems, ellipsoidal, spheroidal coordinates, and those definitions are given in Happel and Brenner. That's a good source for curvilinear coordinate systems in general, and these definitions for stream functions, stresses, surface areas, etc. Okay. Any other questions? So what happens as the Reynolds number increases? So this is a series of pictures that I took from a beautiful book called Album of Fluid Motion by Van Dyke, a Stanford University professor in mechanics. So he collected photographs from different people, from different researchers, and assembled it into a small book, only with pictures. And this sequence of pictures tells us what happens to the flow as we increase the Reynolds number. Okay? We are going to increase the Reynolds number by simply increasing this approach velocity u. So in the first case, you have a Reynolds number of 0.16. And the way that we visualize these is you have a sphere that is fixed, and you have fluid that is flowing past it, and you disperse finely dispersed particles, aluminum dust, for example, 2 micron, 3 micron size, so that they don't settle out. They follow the path of the fluid pretty accurately. Then the reflected light will enable us to see. And you can see even at a Reynolds number of 1.5, the flow is pretty uniform. These are the streamlines that you would see here. Okay, and 9.6, there you begin to see something funny happening at the back. Okay, but clearly when you go to 26, you do see this. That's called a wake, and that means there is a recirculation there. The streamline comes and separates from the solid line. So in the previous case, if you remember, the streamline, the zero streamline is this. So a streamline that is next to it, close to it, will just follow the path and then come back and hug behind and then continue like this. Whereas when the inertia becomes dominant, the particle, the fluid particle that is coming around will start leaving that. So the streamline will actually be now like this. Those are all zero streamlines. So the streamline that is slightly away just separates from the sphere. So there is a separation point that you will see here. There are two separation points in that cut. Actually, separation would be a kind of a circular projection on the rear of the sphere. And these eddies, this particular photo is very nice at 41, stretch in length. As the inertia becomes larger, the eddy length increases. The question is, can we predict all these from Navier-Stokes equation? Not the Stokes equation, because Stokes equation won't be applicable for Reynolds number of 41, but for the Navier-Stokes equation. Today the answer is yes, we can just go to COMSOL and set up the problem, and it will give you exactly the same picture that you see here. People have done that all the way up to Reynolds number of 400, 500 or so. Okay, and you can measure, for example, what is the wake length in an experiment and compare it with the prediction, and you will find that it agrees very well. Okay, but if you increase the Reynolds number to even higher value, 2000, you see the flow becomes, that's what you would call a turbulent flow. Okay, so this is a turbulent wake behind more like a cylindrical object, and the complicated phenomena occurs, something called a vortex shedding. So these waves oscillate behind this. And so the question is, can we try to extend the Stokes solution at least to somewhat higher values of Reynolds number? And the answer is, it's very difficult without computers. That's why computational fluid dynamics emerged as a way to address these questions through using computers to solve the Navier-Stokes equation. Yeah?
In the last picture, where is this obstruction? Is it the
the obstruction here is basically the dark object that you see there. Okay, so it's some sort of an ellipsoidal object that you will see there. Any object that you place in the path of a flow will cause these kinds of separations and wakes, whether it is a sphere or a cylinder or any cube or whatever. And the literature is full of these problems. People have studied them experimentally using laser Doppler anemometer and studied them numerically using CFD as a tool. But we are going to see analytically what happens. In the next course, I think the next year when I'm teaching a course on computational transport phenomena, I will emphasize more on the computational parts. But here we are just looking at the analytical ways as much as possible. So I've told you what is possible with COMSOL, but we won't delve into that anymore. Okay, so one of the first things that we need to do is examine whether this solution that we obtained, the Stokes solution, is uniformly valid. What do I mean by that? The stream function that we have, is it valid for all values of radius as you go far away from the surface of the sphere? Now, there is the film by G.A. Taylor. I don't know how many of you have not yet seen it, but I cut a clip out of that deals with, can you?
In the next experiments, we will look at the resistance of solid bodies at low Reynolds numbers. Two brass spheres in syrup. They have diameters in the ratio of 2 to 1. We'll release one now and the other later.
What do you think would happen in this experiment? This is the Stokes drag. This is low Reynolds number flow, and all we have is there is no wake, and the two spheres are settling.
From the smaller ball, has one more unit to go, the larger one is released. They reach the bottom mark at the same time.
Why?
Terminal velocity.
Hmm?
Terminal velocity.
What about the terminal velocity?
Acceleration becomes zero. Velocity is constant.
Right. So both of them reach a terminal settling velocity very quickly, within microsecond of the time that you release. Initially, you are holding them. When you release it at time t equal to 0, within a microsecond, they will reach a terminal settling velocity. And then it is settling at the terminal settling velocity throughout. So what did you observe? You observed that the bigger sphere settles faster than the smaller sphere. Okay. Let me ask you a physics question. If I did throw these two balls from the Leaning Tower of Pisa, what would I have observed? Do you know that experiment that Galileo, I guess, did? What should happen to those particles if they settle in a vacuum?
There was an attraction between them.
Hmm?
And
You?
I think they should have the same acceleration and the same velocity.
Exactly. Others should review your physics. This is a very basic thing that you must have done in elementary physics. It's a very classic experiment, okay, where he dropped an iron ball and a feather, and they both settle to the bottom at the same time. Why? Because they go through the same acceleration. They are both acted on by the same gravity, right? Why are they different in this case? Why are they settling at different times? Because of the dominant role played by drag. Okay, so it is actually, it looks like none of you have seen this film, or at least this part of the film. Has anybody seen this? No? So all this extra material that I gave on the web is really not useful. All right, so let me continue this. So here,
The drag of a falling sphere is proportional to its diameter and to its speed. The net weight of the sphere is proportional to the cube of its diameter.
why? Explain each one. We just derived the expression for drag in the last lecture. What was it? 6 pi mu ud. Okay, throw the 6 pi, just says it's proportional to mu and the velocity, the viscosity, the velocity, and the diameter. Net weight is proportional to dq. The net weight, what does he mean by net weight?
Gravity minus buoyancy.
Gravity minus buoyancy. Okay, so it's a balance between these three forces: drag, buoyancy, and gravity. When you write that equation, that's how you get your terminal settling velocity. So the velocity that appears here is the terminal settling velocity. Okay, so these two must equal. Okay, why does the net weight depend on dq? Because the volume depends on dq. What is the volume of this sphere? 4 over 3 pi r cube or dq, right? So from these two, can you explain why the bigger sphere settled 4 times as fast? It was only twice as big. If you equate these two, you will say that the velocity is proportional to d squared. Okay, that is the beauty of analytical solutions. You can get the functional form, so you can explain this behavior. Whereas if you're using COMSOL to do these solutions, you can certainly obtain the solution for much higher Reynolds number, but you don't get these intuition. You don't have an easy explanation of why the velocity depends on d squared. Okay, but here is a very clear explanation of that.
The velocity is therefore proportional to d squared. They have diameters in the ratio of 2 to 1. So the larger one folds itself 4 times as fast as the smaller.
This is another important point I want to observe.
Numbers, the disturbance produced by a moving ball extends many diameters, so that beads far from the ball are moved by its passing. Thus, the presence presence of a nearby wall can be important. Here are two identical balls, one near a wall and one far from it. The ball near the wall falls more slowly. Incidentally, it remains at a constant distance from the wall, a consequence of reversibility.
So, do you have any questions on that observation? Okay, let me slide past to
Isolated and will fall faster. Of course, they fall with this influence on one another.
So here he is talking about many particles. So this is a suspension. And why does the suspension settle? How does it settle? But I want to take you to the final part.
One travels half as fast as the vertical one.
So here he has two cylindrical rods. One he places in the vertical direction, other one he places in the horizontal direction. What would be the drag on those? Do you think one will settle, both will settle at the same time, one will settle faster? What does the orientation tell you? Orientation is good. Okay, that's what happens, and he says he shows why it settles twice as fast as the other one. The solution to this is more difficult to obtain because this is a finite cylinder from the Stokes equation. And then he uses this later on in the part of the movie to explain how microscopic organisms derive their thrust. How can they move in low Reynolds number flow? Because if you remember, there was another video that I showed at the beginning where he talks about the kinematic reversibility of low Reynolds number flow. If you apply a force, the fluid will move one way, but if you reverse the flow, fluid will trace back exactly the same path. So if you have, for example, a fish that is trying to swim, this kind of a motion will cancel each other out. Okay, so in the case of a fish, the Reynolds number is much higher, but in the case of microscopic organisms, that kind of motion is not going to give them the thrust. So they have a long tail, and the tail has some sort of a complicated motion that derives the thrust from there. And that's a nice explanation of how microscopic organisms derive their thrust. How can you explain that in terms of low Reynolds number hydrodynamics? So I would encourage you to look at this video because it's a really, G.A. Taylor is one of the foremost minds in fluid mechanics, and this video is done very well. Getting back to it, one of the things that I wanted you to see is that when you have the sphere settling, he had a lot of these colored particles that are neutrally buoyant, so they're not going to settle, but they move. As the fluid moves, they move. So the point that he's trying to make is that the effect of this moving sphere is felt many diameters away from the sphere, 8 to 10 diameters away from the sphere. So the question, I guess, that we are going to address here is, are the solutions that we have obtained for stream function valid at those large distances? So is the solution uniformly valid from r equal to a to r equal to infinity? And the answer to that turns out to be no. Okay, and that is a clue to constructing something called the singular perturbation methods, which was developed by applied mathematicians in the 50s to extend the Stokes solution to beyond this. But the way that we are going to analyze is the following. It's a very ad hoc hand-waving argument. I'm going to take a typical inertial term from the left-hand side of the Navier-Stokes equation. There are many terms. There are 3 equations. Each equation has several terms. But I'm just going to take one term, rho times VR dVR dr. And then I know already what VR is. I know the solution. So I can plug that solution, which is what I have done here. Okay, this one is basically that term. And similarly, dVR, after this whole thing, after you take the derivative, you get this one. Okay, so you're just plugging in the velocities, taking the derivatives, and since it's an order of magnitude analysis, we are going to ask which is the dominant inertial term. Inertial term obviously has products of several things. For example, It's a product of 1 plus 1/2 a over r cubed minus 3 over 2 a over r times these. So if you take a over r, what happens as r goes to infinity to that term? It goes to 0, but it goes to 0 very rapidly because it is cubed. Okay, and if you take r to the power 4, that will go to 0 even faster. So we want to see those terms that go to 0, we don't worry about because they don't contribute anything to the stream function. Okay, so we want to see which is the term that is growing the slowest of all the terms that we have, and that turns out to be the product of 1 with 3 over 2 a over r squared, because 1 with a over r to the power 4 will go to 0 very quick. Okay, so that combination is the only one that's going to grow the slowest of all the terms. Other terms will go to 0 faster. So that is the term that we keep, just an order of magnitude. Okay, so that is the dominant inertial term, and we're going to do the same thing for the viscous term. Okay, so select a typical viscous term and plug in the velocity field that you have, Vr, take the derivative, and what you get is a typical viscous term which goes as r to the power 5, 1 over r to the power 5, whereas the inertial term goes as 1 over r squared. So does the inertial term go to 0 first, or the viscous term goes to 0 first? The viscous term will go to 0 first, right? So when you take the ratio of these two terms, the inertial term to the viscous term, you will get, there is a ratio of this number to this expression to this expression. And you can rearrange that as Reynolds number times r over a to the power 3. So it actually is not going to 0. As r goes to infinity, r goes to 0, even though you may have a very low Reynolds number situation, r going to 0, even in that case, if you take Reynolds number as 0.001, then as you go far away from the sphere, this goes to infinity. Okay, so the solution, we say, is not uniformly valid. The solution is good near the sphere. The solution is not good far away from the sphere. And the reason why the drag force agrees well with experimental measurements, that's just 6 pi mu UA, is because it depends only on the gradients on the surface of the sphere. So our solution near the sphere is fine, but far away from the sphere is not fine. And this idea gave rise to the need to construct solutions in two domains. One solution that is valid close to the sphere, and another solution that is valid far away from the sphere, and then you match the two. So this method is called the matched asymptotic expansion. We are not going to do that because the math involved is quite tedious for us to deal with in this course. Okay. The other approach, well, this is one of the approaches. It's called the perturbation expansion. This idea is fairly simple and very interesting because it's applicable for a number of other problems in reaction engineering, in heat and mass transfer as well. So the idea here is the objective is to extend the solution to higher Reynolds number. Okay, and how do we do that? We do that by breaking up the problem into a series of simpler problems that we can solve that are valid for progressively higher and higher Reynolds number. So we go back to the full Navier-Stokes equation now, not the Stokes equation, because we know that we cannot drop RE term out. If we drop the RE term out, the solution we get is valid only up to 0.1 Reynolds number. We want to improve that. Okay, so we need to keep that. But if we need to keep that, we cannot solve it analytically because we have a nonlinear term, the product of V here. Okay, so this technique of perturbation expansion linearizes the problem as a sequence of linear problems. The idea is very simple. What it is we are going to construct the total solution V tilde as a sum of many different solutions. The first solution is a superscript V0. The second solution is V1. Now V0 is a function of r and theta. V0 contains two velocity components. Okay, and similarly V2. So these are all unknown functions, vector functions, functions of r and theta. But they are multiplied progressively by RE, RE square, etc. Those are Reynolds number parameter we know. We know the numbers. Okay, and we do the same thing for pressure. So the pressure is the lowest order solution is P0. This is called the first order solution P1, the second order solution P2. but they get multiplied by RE square. So this sequence obviously is converging as RE goes to 0, right? As RE goes to 0, what can you say about the magnitude of this term compared to the magnitude of this term? The RE square term should be smaller as Reynolds number is small. But if you go to very large Reynolds number, this will break down because the series will be divergent. Okay, so any questions on that? So that is a conjecture that we can construct a solution to the total velocity and pressure field as a series solution in a perturbation parameter. The parameter that we are perturbing here is the Reynolds number. Okay, so we take these definitions. We take these definitions of Reynolds number and plug it into the Navier-Stokes equation for pressure and for velocity. Okay, so these things are fed in there, both the pressure and velocity expression. And I have shown you how it looks like in the next line. So on the left hand side we already have an RE, that RE survives, and then we have a V. I replace that V by the series expansion, and then I have a dot product. Okay, the dot product there, that stays as a dot product there, and then I have a del operator operating once again on V. That series expansion is plugged in again for the V. On the right hand side you have minus gradient of P. This series expansion is plugged in for that P. Okay, plus del square, the del square appears there, and then that series expansion is for V once again. So we have an equation that is in terms of a series expansion. It is a full Navier-Stokes equation. Okay, next thing that we do is we collect terms of like order, that is order of RE to the power 0, RE to the power 1, RE to the power 2. Collect those terms from the series expansion. Okay, so for example, if you take RE to the power 0, do we have any contribution from the left hand side? The left hand side is this entire term, the product. Okay, when you expand that, what you would have to do would be take V0 dot del V0, V0 dot del V1, V0 dot del V2, etc. But then you'll also get the first term RE, the second term RE square, the third term RE cube. Okay, and then you have to do the same thing with RE V1, V1 with del V0, V1 with del V1, etc. So this is going to be a very long expression. But what we are going to do is collect terms that have the same exponent of the Reynolds number and group them together. So these are all grouped terms from that series with a dot 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 to indicate that there are even more terms in the series. Is that idea clear? That is the central idea of a perturbation series expansion. That we can propose a solution in terms of a perturbation parameter, a series expansion in terms of the parameter. In this case, it's Reynolds number. Take that proposed solution, put it into your original equation, and separate the terms according to the like powers of RE to the power 0, 1, etc. So in the very first term, none of the terms from the left hand side will contribute. But on the right hand side, you have delta P0 and del square V0. None of them have Reynolds number in it. Okay, so RE to the power 0 is 1. There is no Reynolds number in there. That's how you get these two terms. Is that clear? Yeah. Plus, then I start collecting RE to the power 1 term, and I want you to now tell me how I would get these terms that you see in the parentheses. How do I get this term V0 dot del V0? V0 dot del V0 multiplied by RE. Is there any other term that has RE in it? RE alone? No. So that is the only reason that we have only this term. On the right hand side, we have RE here. So it is del P1. And then you have RE there. So it's del square V1. Okay? You get the idea now, right? And you need to do the same thing for RE square. It gets a bit more complicated when you go for RE square. Okay? When you go to RE square, what happens? You will have RE here multiplied by another RE. So that term could survive. Okay, so that is V1 with V0 or V0 with V1. Both of them will give you RE square. But V1 with V1 will give you a RE to the power 3 term, which will appear in the next expression. Okay, so the only thing that appears is V1 del V0 or V0 del V1. On the right hand side, you will have P2 and V2. So delta P2 del square V2. And the series continues. I'm just indicating that by this dot dot dot, meaning it's an infinite series. That is equal to 0. Okay, so if you understand from this step to this step, then you have basically understood the idea of a regular perturbation expansion. Okay. Now what we are going to do is, of course, P0, V0, P1, V1, P2, V2 are all unknown functions, but we are going to derive equations for them. The argument is, since this must equal to 0, but Reynolds number is not equal to 0, right? So we must have the terms that are in the parenthesis, like this term, or this term, or this term. Each one must be equal to 0. Okay? So that gives you these equations. Since RE is not equal to 0, each term in square brackets must be 0. So from the first expression, you get this is equal to 0 as an equation. That is, we recognize as the Stokes equation. We have already solved for it. We already know P0 and V0, the solutions for it. Okay? So the next term will have P1 and V1, but V0, I move it to the right hand side. Why? Because by the time I come and solve for P1, V1, I already have solved for V0 and P0. So the right hand side is a known quantity. So this is known from the previous solution. So the nice thing is the previous solutions feed on to the next solution. So I can construct this in a series of iterative way. Okay? And the same thing from the third term, P2 and V2 are unknowns. I keep them on the left hand side. And I move V1 dot V0 plus V0 dot del V1 to the right hand side. By the time I come to solve for P2 and V2, I would have already known V1 and V0 from the previous two steps. Okay, let me ask you a question now. What have I done in doing this breaking down the problem? I have linearized a nonlinear problem. Okay, so at this stage, when I had the full Navier-Stokes equation, I had a nonlinear problem in here. So if you look at the series of problems, I have not one problem now, I have a series of problems that you need to solve. But on the left hand side, they all have the same operator, del P0, del square V0, del P1, del square V1, del P2, del square V2. What does that tell you immediately? If the operator on the left hand side is the same functions that you found out as a solution should satisfy those if you take the homogeneous part. Okay, that is, set the right hand side equal to 0, you already know the homogeneous part of the solution for everything. But you need to take the basic solution and feed it into the next level, and feed it into the next level, and find the particular solutions for each case. Okay, and this process can be automated with symbolic processing tools like Maple. Okay, so that's why this became very popular in the mid-70s. Van Dyke again published a series of papers where he showed that automated algebra programs can solve these analytical things up to 20, 30 terms. But there were other mathematical challenges that came out from extending the series to that level. There are some singularities in the solution that he needed to take care of. So that method really, once the computers came in with the CFD, these methods kind of went away. But still, the basic solution gives us an insight that it cannot be obtained from a computer solution. Any questions on that? Yeah.
How you did that series expansion?
That's a good question. How did I write this part? That's what your question is. I just wrote that, and there is no. The real answer is there is no unique way to write that. Okay. Here, because Reynolds number is the parameter, and Reynolds number is a small parameter, by writing it as RE squared in a naive way, just a series expansion, I'm proposing that as a solution. I can find certainly P0, V0, P1, V1, P2, V2 that will satisfy that series. The other way to ask the question is there another series that I can write and find a solution? Why can't I write, for example, V0 plus square root of RE V1 plus RE to the power 3 over 2 V2, etc. There is no uniqueness to this process. That's a very good observation. Okay, so there is a degree of arbitrariness in the way that I write the series expansion. It comes from a certain expectation about the parameter. You typically do the expansion in a parameter that is small, and then typically you just use an algebraic expansion like that. Okay, but unless you know something more about, like in boundary layers, for example, you know the boundary layer goes as square root of Reynolds number, the boundary layer thickness. Then you might use that information in constructing your series.
And V0 is you get from the Stokes.
Yeah, yeah. So V0 is the Stokes solution. We already have solved for it. So if you want to solve for the next one, you take that, you can evaluate the right-hand side, plug it in, and then you can solve the next one. It turns out that this regular series expansion, when you solve for the next one, you cannot satisfy the boundary conditions. You don't get a solution because of this problem of lack of uniform validity of the solution. The solution that you have for V0 is not uniformly valid over the entire domain. So that error creeps into the P1B1 solution, and the method breaks down for a sphere. But the method has been applied for other shapes, like cylinders and other shapes. Did you have a question?
Yes. You said this perturbation is good for the small parameter Reynolds number here. So does this necessarily valid for large Reynolds number?
Well, the thing is, if you are looking for a series solution in the large Reynolds number, you can always redefine the problem as define another parameter, epsilon, which is 1 over Re. So as Re goes to large, epsilon goes to small value. Then you can construct a series expansion in terms of epsilon, for example. Right? Yeah, it's a good question. So that's just the idea. It's not in your textbook, but it is a book by Morton Den, Process Fluid Dynamics, as the series expansion method introduced in there. Another way of linearizing, the thing is analytically we can solve only when the problem is linear. Okay, so all these methods are ways of linearizing the problem. The first one that I presented is just a strict mathematical series expansion. The other one uses physical intuition to carry out the same linearization, and it was done by Ausseen. And you will see this name if you work in fluid mechanics area quite often. It's called the Ausseen solution. The basic idea here is the following. I have a sphere, and I have a free stream that is approaching u. Okay, so this velocity is deflected by the presence of the sphere. So the deflection from this is departure from this is going to be small compared to the mean field velocity. So what I can do is I can split my velocity component into two parts. One is the free stream velocity. The other one is a small deviation from that. And the deviation is caused by the presence of the sphere. The sphere is not there, the deviation will be 0. Okay? So these deviations are considered to be small, caused by the presence of the object. That's in the u direction. In the v direction, there is no component of the velocity in the v direction, the main component. So v prime is only because the sphere is there. Its presence creates these disturbances. So we call these disturbances u prime, v prime, w prime. If you take the sphere out, the velocity field is going to be only u, free stream velocity. And he took these definitions and put it into the Navier-Stokes equation. Okay, so I'm showing you here the x1 component of it in Cartesian frame. Okay, so remember we have this term v dot del v. When you expand that, you're going to get v1 dv1. I guess I'm using uvw, so let me write it like this: du dx1 plus v du dx2 plus w du dx3. That's what, for the x1 component, that expansion will result in. So wherever I have u, I substitute u plus u prime. Okay, so these are the terms u there in that expansion. And wherever I have v, I do v prime because v is v prime. And wherever I have w, I put w prime. Okay, and then I use the argument that whenever I have product of two small numbers, it's going to be smaller than the individual number. Okay, so v prime, w prime, u prime are deviations from the main velocity, they are treated to be small numbers. Okay, so any product that I have, for example, between here, I'm going to neglect that. Similarly, V prime with U prime, I'm going to neglect that. W prime with U prime, I'm going to neglect that because there are products involved. That is a linearization process. The other thing that you need to notice is U is not a function of X3, so that drops out. U is not a function of what did I do? U. Yeah, U is not a function of X2, and U is a constant, right? U is not a function of X1 either, so that drops out. Now, I cancel here U prime and U prime, but what I cannot cancel is, that's where I got my train of thought lost, U with U prime. Okay, so that is the only term that survives, U on the outside, d dx1 of U prime. Okay, so that is the only non-zero term from that expansion by this linearization. How did I achieve the linearization? Because I neglected the quadratic terms, because I said that they are small products of small numbers. So U is a constant in here. That's what linearizes it. Previously, I had V1 dV1 dx1. I basically replaced that by U dV1 dx1. Okay, so this is now a known velocity field, a constant number, so that equation becomes linear. So he linearized the Navier-Stokes equation and obtained this equation in index notation. Rho U dui prime dx1 equals minus dp dxi on the right hand side plus del square ui. So I equal to 1 to 3. This is called the Austen equation. Okay, it's not Stokes equation, it's not Navier-Stokes equation, it is somewhere in between. And this is linear, so he could solve that. Again, the solution for this is even more complicated than the Stokes solution, because you need to carry now this linear term on the left-hand side. But what he obtained was this correction, 3 over 16 times RE. Okay, and it turns out this is not a very good correction, because it increases the validity from 0.1 to maybe 1. But if the Reynolds number is higher, then the other terms are still important, so you cannot ignore them. Any questions on that? So the idea of an Austen linearization is to assume that the mean field U, the mean velocity U is the dominant one, and the U prime, V prime, W prime are treated as perturbations from that mean velocity, and because they are small, drop out all the products in the Navier-Stokes equation, and that gives you a linearized inertial term. So we are still keeping the inertial term, only the dominant one. Now, the next thing that we need to ask ourselves is, okay, we've spent a lot of time obtaining the solution for a sphere. Can we do that for a cylinder? Okay, so if I have a cylinder and a flow past it, how does the problem change? The symmetry is different. Previously, we had axis symmetry, right? Here we have a symmetry in the axis direction. So we still make it two-dimensional. We still have the r theta coordinate, but we have a z coordinate. Okay, so this is x, y, z. Along the z axis, there is no change. So we are making it into a two-dimensional problem. Now, this problem is also a very rich literature. There are probably thousands of papers on this. It turns out that when Stokes tried to solve this problem, there was no solution to Stokes equation. If you take the Stokes equation and try to solve this, and I will show you why, there is no solution, and that is called the Stokes paradox. Okay. Now, there is a dimensional argument that people have used since then to explain why that is. For example, in a 2D flow, you can ask the question, what is the force F? Force per unit length, because this is an infinitely long cylinder, so you need to talk of a force per unit length of an infinitely long cylinder. Okay, so what does that force depend on? It obviously depends on the radius of the cylinder, depends on the approach velocity of the fluid, and it depends on the viscosity of the fluid. A very common problem, let me ask you this, a digression. In power lines, those are basically cylindrical rods, right? Very long cylindrical rods. And if you have a wind, you can hear a sound sometimes, a humming sound. Has anybody experienced that? Near power line, when there is a wind, there will be a sound, kind of a sound. What is that caused by? Everything in nature has to be fluid mechanics, not a fluid dynamicist. It is a fluid dynamical phenomenon. It's an interaction. Yeah?
That has something to do with the electric in the lamp.
Um,
No.
Also,
I think
the electrical, it could be, you will find that noise near transformers. But if you go to a field where there is no transformer, but there is a wind, it will have a very similar hum. And it is caused by something called the fluid structure interaction. That is, the fluid that is flowing past it causes the wire to vibrate. And if it vibrates at high enough frequency, it can create a pressure wave. What is sound? How is sound transmitted? Through fluid. Without the fluid, you don't have sound transmission, right? So it's the pressure pulses that travel, and that is the one that creates that sound. Now, we are going to talk about later on this vortex shedding phenomena, and that also has a frequency of oscillation in the flow. And if the sphere is rigid, fixed, but if the cylinder is not fixed, then the cylinder itself can oscillate in response to the applied force. Okay, that's a digression.
Like a vibrating beam or something?
Pardon me?
Like a vibrating beam or something?
Vibrating beam, yeah.
Okay.
So beams that could vibrate, it's very common. The shutters that, for example, that vibrate in a wind. Okay, so whenever there is a fluid that is interacting with a structure that is not rigid, that has some flexibility, you might get into this fluid structure interaction. In fact, there is a movie, I think I put it on the web, about a very famous bridge that collapsed.
Oh,
How many of you know about that?
bridge. I don't remember it. It vibrates so much that
the
like
resonance,
The resonance. You know, well, what is resonance?
so when something sets an object into its own frequency.
Right, there is a natural frequency for the structure, and if you force it at the same frequency by the wind, then the energy basically just gets accumulated and amplified. Right. And that is also a failure caused by a fluid structure interaction. Okay, you need the wind velocity, otherwise it's not going to, the bridge is going to be happy, stagnant there. Okay, all these phenomena are related to solutions of the Navier-Stokes equation in flow past objects. Okay, so when I talk about an infinitely long cylinder, it may look like very ideal thing. Where do we see an infinitely long cylinder? But you can relate it to daily experiences that we have. Getting back to this, because it's an infinitely long cylinder, we can express the force per unit length. That is the only thing that we can meaningfully talk about. And that depends on these three variables that I have identified: the viscosity of the fluid, the velocity, and the diameter of the cylinder. So if you do a dimensional analysis to form a dimensionless group out of this, using Buckingham Pi theorem, turns out that this is the only dimensionless group that you can form, F divided by mu u. Okay, that says that must be a constant, because there is no other dimensionless group I can relate that to. So that means that F divided by mu u must be constant. It must be independent of A. That means no matter what is the diameter of the cylinder, I will have the same force. And that is not true. That's not intuitively true. That's not true as we can get from the solution as well. So the problem manifests itself even in simple dimensional argument when we try to put these variables into dimensionless groups, and we find with this contradiction that F over mu u, the dimensionless group, must be a constant when we know that it is not. Now, if you introduce a finite length to the cylinder, okay, so the radius is A and the length is B, Then you have a dimensionless, another dimensionless variable, which is A over B, the ratio of the diameter to the cylinder length. That means this can be some function of that. So as you change the length or the diameter, the drag force will change. Okay, so that problem has a valid solution, but this problem of an infinitely long cylinder does not have a valid solution, and that is called the Stokes paradox. Why is that? We can solve the same equation, the Stokes equation, but this time this E square has to be expanded in cylindrical coordinates. And the book by Burt, Stewart, and Lightfoot, they give you the expansion for E square in cylindrical coordinate. Previously we saw it in spherical coordinate. Okay, so take that and go through exactly the same process that we did in the class. So propose a solution of the form that has sine theta now, because what you need to do is resolve the far string boundary condition u in terms of ur and u theta in cylindrical coordinates. Okay, and you will find that this is again a good exercise to reinforce the mathematical steps involved. I'm just giving you a very quick overview of how this is done. So the starting point of the equation is the same, but in cylindrical coordinates. This equation is the same, but in cylindrical coordinates. And that's given in Burt, Stewart, and Lightfoot. Okay, and then you need to construct the boundary conditions on the cylinder far away from the cylinder. Those are the useful exercises that you can do on your own. But when you go through this, you get a solution for stream function past a cylinder, flow past a cylinder, that has this form. Of course, in always cylindrical coordinates, you get a log r term somewhere, right? So you have a r cubed b r log r plus c r plus d over r. So there are 4 integration constants. Okay, and the boundary conditions turn out to be: for stream is u r sine theta, on the surface stream function is 0, the derivative of the stream function is 0. But the problem is the far stream condition, as r goes to infinity, dictates that this term should be 0, because this goes as r cubed. We cannot have that because we know that it goes only as r. Okay, so that determines, in fact, c must be equal to u. Then it matches with r. But this term r log r also goes to infinity at a much faster rate than r. Okay, so we cannot have that too. So we must have a equal to 0, b equal to 0, and c equal to u. So from that one condition, far stream condition, we have determined 3 constants. We still have 2 conditions to satisfy, and we have only 1 constant. So there is no way that we can satisfy that. And that means that there is no solution, there is no function for psi that will satisfy the differential equation and all the boundary conditions. That means that there is no solution for that particular problem. Only for creeping flow limit. Once you put in the inertial term, the problem will go away. Okay? So this is called the Stokes paradox, that for cylindrical flow, there is no Stokes solution. Any questions?
Is there a way to solve it for cylindrical without using the like the E squared like he uses?
Good question. There is no way. The answer is there is no way. Whatever variable that you solve for it, you will get into a problem one way or the other. What are the other choices? The other choices is you can try to solve it in terms of VR, V theta, and P. We have the 3 equations, continuity and 2 momentum equations. You can try to solve for them directly in terms of those velocities. And you will get into this problem of not being able to satisfy all those 3 equations and all the boundary conditions. So the problem does not manifest just because we transform the variable into psi. The problem is fundamental to this particular situation. And that comes out when you do the dimensional analysis also. Okay, already there is a clue from the dimensional analysis that there is no way that you can have f over mu a to be equal to a constant. Okay. Now, a whole course can be taught on solution to this Stokes equation. And there are 2 very good books, Happel and Brunner and Kim and Karipalla, I think. But we are going to just end there because we have seen what Stokes flow is, and it's typically valid in low Reynolds number flow, but there are a lot of situations where we do have low Reynolds number flow. Particularly these days, microfluidics is a very dominant field where we try to devise entire lab on a chip analytical techniques on microchips that are etched with channels that are micron sized, 30 micron, 40 micron size. And I don't know how many of you are still young, so you won't know about blood sugar monitors, but I do occasionally use that. Has anybody seen blood sugar monitors? No? It's basically, they sell these for about $100 or so. And you can buy these strips. And all you have to do is prick your finger, take a sample of blood. Glucose monitor.
Sometimes it's
So all you do is take the blood and then put it on the tip of that small strip. That's a microchannel. So that takes the blood into the device where there is a detector. And it detects the amount of sugar and instantly gives you the answer, right? That kind of a device is being devised for many, many areas in chemistry, in biology, etc. Where if you want to separate cells or if you want to do DNA diagnosis, DNA sequencing, all these can be done on these microfluidic devices. But in all these devices, the Reynolds number is low. Why? Channel dimension is low, the velocities are low. The advantage from a practical point of view is you need very small samples. Okay, but the mechanics of that is fairly interesting, and I'm giving a course. This is a plug for my course next term on microfluidics. Okay, the entire course is going to be electrokinetic transport phenomena. How does the transport occur in such microfluidic devices? Building up on what we see in this course. So as I said, the whole course can be given just on low Reynolds number hydrodynamics, but we need to cover a lot of other areas in this course. So we're going to look at the other extreme. We have seen rectilinear flows, one-dimensional flows where we can get analytical solution, and we have seen low Reynolds number flows, and now we are going to see very high Reynolds number flows, and we will see the deficiency in both. And we will see boundary layer theory as a theory that beautifully merges the two. And with that, I think we will probably be at the end of the course when we reach there. We need to do a similar thing for heat and mass transfer as well. Okay. Now, the ideal fluids or potential flow in 2 dimensions is about the other extreme, very large Reynolds numbers. Okay. And again, Navier-Stokes equation is the starting point, but we assume the fluid to be ideal. What does that mean? Ideal means it has no viscosity, no friction. It's just will slip by any solid surface. Okay, so its viscosity is 0, and you will see on the right hand side, the viscous term is dropped out. What we should have added is mu times del square V, but we just dropped that out. And there are many names by which it goes. Ideal is one, inviscid is another one. 0 viscosity, inviscid fluid. So this viscous term is set to 0. And that equation is called the Euler equation. They are all derived from the Navier-Stokes equation. Okay, the Stokes equation, the Ausseen equation, the Euler equation, and then we will see Prandtl boundary layer equations. They are all subsets of the Navier-Stokes equation, valid in different domains. So in this case, this is valid in the domain of RE going to infinity. Why do we say that? Because RE is dV rho over mu. But I've said mu goes to 0. Viscosity goes to 0. It's an ideal fluid, 0 viscosity fluid. So when mu goes to 0, Reynolds number must go to infinity. Okay? So we are approaching the problem from the other end. Now, when you have that, can I impose the no-slip condition? We cannot. No-slip condition is a consequence of viscosity, friction, where if the solid is stationary, fluid next to it must stick to it. It must also be stationary. Okay? But with the ideal fluid assumption, that's not possible. So we have to give up on the no-slip condition. But we can still impose this condition, which says that the normal velocity to a solid wall is 0. That is impenetrable. You can have an ideal fluid that can slip past, but it cannot penetrate the solid. Okay? So u is the velocity of the solid. Take its normal component and set that equal to the normal component of the fluid velocity. So the right hand side here is the solid velocity, and the left hand side is the fluid velocity. So they must be continuous. If the solid is moving, fluid should move with the same normal velocity. Or if u is 0, the solid is stationary, then the normal velocity must be equal to 0. So that solution to that is again a whole course. And there are books on the ideal potential flow. Okay, but we just want to learn the techniques for solving two-dimensional potential flows. Potential flows particularly have been very successfully used in aerodynamic design, okay, because they cannot predict shear because there is no shear, okay, so they cannot predict the drag, but they can predict the pressure profile around objects fairly accurately, okay, and we need to understand the reason why does it predict the pressure but not the velocity, and the boundary layer theory will tell us why that is. Okay, so, and in calculating lift forces, all we need is the pressure distribution around an object, and you resolve it in the vertical direction, and if there is an imbalance in the pressure between the top and the bottom surface, that's your lift force. So in aerodynamic, in optimization of the shapes of aerofoils, for example, potential flow is used very well. And people have measured the pressure profile on various aerodynamic objects and then compared it with a solution to the Euler equation. Okay, and they agree quite well. So that's one of the motivations. Yeah.
So because here we assume the fluid is to be ideal, so there's
Yeah.
no stress.
Yeah.
But in reality, that's the lower stress contribute to the lift force.
No. There is a small contribution from terms like tau xx or tau rr, right? But the dominant term turns out to be the pressure, because when you see the T, it is minus IP plus tau, right? So the total stress depends both on the pressure and the shear. Here we have thrown this out. So the question you can ask is, does that introduce errors in the lift force calculation? And that turns out to be very small. There is an error, but it turned out to be very small. Only when you are considering the pressure profile. Okay, the pressure profile is accurate, so the lift force that you will calculate from the pressure profile is very close to what you will see for real fluids. Okay, but the drag is not predictable at all, so you need to go and solve the full equation to predict the drag. That's where the boundary layer theory comes in. Good observation. Okay, now what we are going to do is I'm going to give you a theorem. It's called the Kelvin's theorem, without proving it. And it is derived for an inviscid fluid, okay, using the Euler equation. So if you apply the Kelvin's theorem, that means you are automatically satisfying the momentum equation, the Euler equations, okay, and that says basically that the vorticity is conserved. Remember, we introduced vorticity, and what is vorticity? It's a measure of rotation of the fluid, okay. So that vorticity is conserved. What does it mean? Let's do a thought experiment. Okay, this is going to be a bit difficult for you to imagine, because I'm asking you to imagine with an idealized fluid. Suppose I have a beaker, okay, and I have a fluid in there, a real fluid, water, okay, and I give you a spoon, and I say, get a vortex in there. What will you do? You will just put the spoon there and stir it, and it forms a vortex. Okay. I don't give you a spoon, but I give you a curved part of a cylindrical shape, something like this, and I say insert that, and you can spin it in the radial direction. Will that create a motion? Will that create a fluid motion if it is an idealized fluid, or if it is a real fluid? Two cases. Are you following what I'm trying to say? With a spoon, it's very easy. The real water, I can spin it and I can create a vortex. Now I'm asking you to stretch your imagination to the situation of an ideal fluid, which has no viscosity. And if I give you a spoon, can you get that fluid into motion, into circulation? You can if you keep the spoon perpendicular to your motion, because you can always apply a pressure, right? So this is going to be difficult for me to explain. Imagine you have a beaker, right? And in the beaker, you're putting a spoon that is kind of aligned in the radial direction, and then you're moving it in the angular direction. So you're applying a pressure. The fluid has to move. Okay, so that will create a vortex. Now, if you are an ideal fluid, I take the spoon. Will it ever come to rest? It will not. Because once you impart the angular momentum, there is no dissipation mechanism. Right? There is no viscosity for an ideal fluid. So it will just keep on spinning forever. And in fact, that is the thing that is captured by this Kelvin's theorem, that the vorticity is conserved. Once you give it a spin, the spin is conserved forever. There is no dissipation mechanism. Okay. Now, going back to the same experiment, now you need to take a part of a cylindrical piece that you would insert into it along the axial direction and then rotate it. So you're basically applying tangential stress, not a normal stress. Will the real fluid move? Will the ideal fluid move? The real fluid will experience shear as this object moves. Okay. Okay, let me simplify this. Suppose I take a stirrer and I have a cylindrical disc that is mounted. Okay, so I take that and I insert it and then I spin the disc. Okay, so the motion is going to be created by this moving cylindrical disc. Now, in a real fluid, that will set the remaining fluid into motion eventually. But in an ideal fluid, what would happen? Solid will just slip because there is no friction, right? So you cannot set it in motion. In an ideal fluid, you cannot set it in motion by simply rotating a boundary in a tangential direction. You need to have a normal force, a pressure force. So the pressure force will set it in motion, but once you set it in motion, the only way you can stop it is by putting this in a normal direction and arresting it. Okay? So that phenomena, basically, you can think of it as being captured by the statement that the rotation, the vorticity is conserved. And vorticity is defined mathematically as del cross V. And whenever you impose this condition that the vorticity is 0, it is the same as satisfying the Euler equation, the momentum equations. Okay. Now we are going to use some vector identities. One of the vector identities is that del cross del phi is equal to 0. You can always prove that no matter what the function phi is, as long as it is continuous, using index notation, you can prove that must be equal to 0. That vector identity compared with the expression that I have here, I can conclude that if I can define my v to be the gradient of some function phi, v as gradient of some function phi, then I will automatically satisfy the irrotationality condition of irrotationality because of the vector identity that I have here. That is why I call this as a potential flow. So I'm defining a potential function phi. Phi is called the potential function, and it's a scalar function. Just like stream function was a scalar function, potential function is a scalar function. And the gradient of the potential function gives you the velocity, and by definition, because the del cross V must be equal to 0, it will always be satisfied according to this vector identity. Remember, we said that using Kelvin's theorem is equivalent to satisfying the Euler equation. So the momentum equation is satisfied, but we still need to satisfy the continuity equation. So we take this definition for V in terms of the gradient of phi and put it into the continuity equation. The continuity equation for an incompressible fluid. Okay, so that is del dot V. So substitute for V by the definition del phi. So you get del dot phi, and that is the same as del square phi. Okay, so these are just mathematical operations, but we need to step back and see what have we achieved here. We started solving the problem with large Reynolds number limit. We threw out the viscous term, and we ended up with Euler equation. And we said the Kelvin's theorem tells us by solving the Euler equation that the vorticity is conserved. So the vorticity del cross V is equal to 0. Then using the vector identity, we say, wow, if that is true, I can always get a velocity field from gradient of some potential function. I don't know what that function is, just like stream function. I can solve for it later, but for now all I know is that such a function exists, and when I take its gradient, it will give me the velocity, and it will automatically satisfy the Kelvin's theorem. It will automatically satisfy the irrotationality condition. Then I take the same velocity field and plug it into the continuity. I get now del square phi equal to 0. So I would have satisfied my continuity, I would have satisfied my Euler equation. But what I need to do is answer the question, what is that phi? Because I just said phi is some function, the gradient of which gives me the velocity. and it automatically satisfies the Kelvin's theorem. And if I impose del square phi equal to 0, I also satisfy the continuity equation. So I must find the value of psi in the phi in such a way that this Laplace equation is satisfied. So once again, from a three-dimensional, this is all valid for three-dimensional flows as well. From a 3 momentum equation and 1 continuity equation, 4 equations, I have reduced the problem of solving for one variable, phi, from one scalar equation, del square phi equal to 0. So any solution that satisfies this equation, it's called the Laplace equation in mathematics. Any function that satisfies the Laplace equation will be a solution to some potential flow problem, because it will satisfy the continuity, it will satisfy the irrotationality condition. So I have simplified the problem quite a bit. Instead of solving four equations, I need to solve only one equation, a scalar equation. Okay. The other thing is the Bernoulli equation. I think we talked about it when we were deriving the energy equation. So we start off once again with this Euler equation. Remember, Euler equation is the Navier-Stokes equation without the viscous term. Okay, mu del square v, that's dropped out. So we are going to use another vector identity, which I gave you at the very beginning when we did the review of the vector calculus. So v dot del v is equal to del 1/2 v dot v minus v cross del cross v. It's an identity that's valid for any function v. And we're going to define g, the gravity, as gradient of another potential function g. So this is called the gravitational potential. Which is nothing but gz. Okay, the gravity g times z. And so we take these two and put it into the Euler equation. So on the left hand side we substitute for this. On the right hand side we substitute for g with this one. Okay, and the pressure remains as it is. So, and then you notice the reason we did this is we want to get everything in terms of this del operator here, the del operator here, and the del operator here. So we can combine all of them on the left hand side. Del 1/2 v dot v plus, when it goes to the left hand side, p over rho. Rho is constant, so I can take it inside, plus g equals whatever I have left with that goes to the right hand side. Okay. Now this is still a momentum equation. So when I dot this with the velocity, dot product with the velocity, force times the velocity is the energy, the work done. Okay, so I can now dot it, and on the right hand side I immediately see that this is equal to 0. Why is this 0? Again, another vector identity. V cross W will be a vector that's perpendicular to V. So when you dot it with V, it must be equal to 0. So that is equal to 0. That tells us that this entire thing must be a constant, because this is equal to 0. When you integrate that, we have a derivative. So when you integrate that, that must be a constant. But the integration must be done carefully. What does this operator V dot del something mean? It's the convective acceleration, Lagrangian acceleration, following the motion of a particular particle. Okay, so the integration has to be done along a streamline, because we know a particle of fluid will follow the streamline. Okay, so along a streamline, this must be a constant. Okay, and that is your Bernoulli equation. So you understand the assumptions under the Bernoulli equation. It is inviscid fluid. Okay, and along a streamline, that must be a constant. I think maybe we will stop there and look at two-dimensional potential flows in the next lecture. Okay.